Hey everyone, so welcome to today's session. Today we're going to be learning about alpha, beta, and gamma radiation. So if you haven't been to one of these sessions before, just to let you know how it's going to work, we're going to split the session into two halves. And in each half of the session, we'll go through some new material, and then we'll review it by doing some exam questions. Before we do that, for the very first slide, we'll just do a little intro, some things it might be nice to have in the back of your head as we go through the session. So a little review panel at the start. So okay, outside of that, feel free to say hi in the chat. I'll also ask questions as I'm going along to see how people are getting on, even when I'm going through the learning stuff. And if you have any questions, please just let me know. I'm keeping an eye on the chat. So please just tell me if you have any questions, and I'll do my best to answer as many as I can in the time that we've got, which is approximately an hour. Okay, so I think we'll pretty much get going just here then. So just a little bit about me. So I'm Matt. I'm the lead physics teacher here at Snap Revise. I was a physics PhD student at Oxford University and have been an A-level physics tutor for many years. Good. Okay, so that's a little bit about my background. And now I'm going to let you know about today's session. So in today's session, our objectives are to try and understand how and why radioactive decay occurs. We're going to try and analyze the properties of the three key radiation types. It's going to be alpha, beta, and gamma. And we're going to try and understand the practical applications of radiation, as well, actually, as some of the practical dangers of trying to use radiation. Okay, good. So let's start with maybe just a little review panel. So here we go. We're going to start by just reviewing a few things, both about nuclear notation and also about conservation laws. And as I said before, if anyone has any questions, just let me know in the chat. Okay, good. Is this lesson from A2? That's actually a good point. I can't fully remember now. I think it probably is. It's particle physics. But I can't actually remember for sure. What we will do in a second after this slide is show the spec points that we're doing for AQA, OCR, and EdXL, so that might make it clearer. Okay, cool. So let's start with nuclear notation. And so a classic example of nuclear notation will involve some kind of a symbol, some kind of number at the bottom, say 6, some kind of number at the top, which is going to always be at least as big as the one on the bottom, and often somewhere near double for small atoms. Okay, so this is a little notation that we use to represent various aspects of an atom. So what is an atom usually? Well, usually it's some kind of nucleus with some protons and, say, neutrons in the middle. And then around the outside, we have kind of electrons, which live on certain shells. And this is typically notation. This is notation that really focuses on this part here, the nucleus in the middle. Okay, so precisely what does it tell us? Well, the number at the top tells us the number of nucleons. Hi, everyone who's just joining. Welcome to the session. We're just doing a little review slide, so we haven't started the proper session yet. I'm just going through nuclear notation. Okay, so what are nucleons? Nucleons are the bits of the atom that actually live in the nucleus. So what it really counts is the number of protons, because those live there in the nucleus, plus the number of neutrons. Okay, this is in opposition to this number here, typically called the atomic number. Often this is called the mass number. This is often called the atomic number. And this one tells us the number of protons directly. So that's why it's going to be smaller, right? Because this is the number of protons. This one here is the number of protons plus the number of neutrons. From this, we can figure out the number of neutrons by subtracting the bottom number from the top one. So the number of neutrons here is going to equal 12 minus 6, which in this case happens to always also be 6. Good, fine. Now, we also have this symbol here. For instance, I've drawn the symbol here for carbon, and this is the element symbol. And really, this doesn't tell you any more information than we had before. So element symbol. Why does this not tell us any more information than we had before? Well, because the number of protons actually determines what the element is. The fact that this atom here has 6 protons means it has to be carbon. Carbon's just a special name for the atoms whose nuclei have 6 protons. But the reason we use element symbols is that numbers are kind of hard to remember in a way that words and letters might not be for us. So when I see the symbol C, I think of this concept called carbon, and that's just an easier thing to organize and keep in my head and talk to other people about than it is to say, oh, the atoms that have 6 protons. Okay, good. Next, let's talk a little bit about conservation laws. So these are laws which are concerned with deciding whether interactions between subatomic particles can happen. So these are about interactions between subatomic or atomic particles. Because we see conservation laws even in Newtonian physics, even in just classical mechanics. There we see things like conservation of energy. And we see things like conservation of momentum. Now, these are quantities that are conserved in subatomic interactions, but we're actually going to focus on some other ones here, which are more specific, that tend to, at least at A level, only really come up for subatomic particles. So those are the conservation laws for charge, conservation law for baryon number, which is a bit like mass, baryon number, and the conservation of lepton number. And lepton number is not really like anything else. Lepton number is this very special subatomic concept. Okay, so let's start with charge. We've got a possible particle interaction here at the top. And often what you'll be asked to do in an A-level physics exam is determine whether this interaction is possible. And when we ask if an interaction is possible, what we're really asking is, do any of the conservation laws ban this interaction? So, for instance, charge is something more recognizable. You may well know that protons always have a charge of +1. The symbol P here is for a proton. You may know that electrons are always negatively charged, so we have a charge -1 here. So the total on this side is 0. Fine. Let's look at the charge on the other side. Now, this is the symbol for a neutron. A neutron has a charge of 0. And no worries if you haven't seen this before, but the charge of this thing here, which is called an electron neutrino, is also 0. So indeed, the charges of both sides here are 0. So for the other examples, we have this thing called baryon number. So the point is that the subatomic particles are split into things like protons, neutrons, and quarks, which are baryons, and things like electrons, electron neutrinos, which are leptons, and they count differently in conservation equations. So for instance, the proton is a baryon, it has a baryon number of +1. The electron has nothing to do with baryons, so it has the baryon number of 0. On the right-hand side, we have a neutron. That's a baryon. It has a baryon number of +1. This electron neutrino thing is a lepton. Doesn't see baryon stuff, 0. So indeed, again, we have our other conservation law being satisfied here with the law having the value 1 on either side. For leptons, it works the same, except it's the electron and lepton stuff that we focus on. So protons don't count here. Electrons have a value of +1. Neutrons don't count. Electron neutrinos have a value of +1. So this lepton number is also a quantity that is conserved. In other words, this is an interaction that can happen. And in fact, this one has a special name. It's called electron capture. Okay, so no worries if that felt a bit fast or a bit unfamiliar. It's a series of things that are good to have in your head for today's session. But I mean, the left-hand side will be especially important. The right-hand side is more like useful background info. Okay, good. So, for someone who was asking about whether this is A1 or A2, I don't know if this makes it clear for them, but here are the spec points that we're going through and the kind of indexes in the syllabus. So you may be able to figure it out from this, but I'm fairly sure it's A2. Here's the OCR spec points, module 6. And here's the Edexcel spec points, which look more concise, but that's always true for Edexcel. Okay, so let's get started proper now, and we're going to start by introducing the concept of nuclear decay. So what's the idea? The idea here is we're going to be studying the nuclei of various atoms. So here's some kind of nuclei here, for instance, with 3 protons, 3 neutrons in it. And sometimes nuclei in atoms spontaneously change into something else. So a classic thing that might happen is one of the protons might become a neutron. So let's say the neutrons are the white circles. It might be that this proton here becomes a neutron. That's a kind of nuclear decay. Something has spontaneously changed in this neutron. Another thing that might happen is that a chunk might just fly off. So you might find that instead this goes to a pair of chunks, something like this, something like this, and they're just 2 separate things now. These are nuclear decays, spontaneous changes in the nucleus. Okay, and we're going to look at a few examples, and the classic example is indeed one in which there's a change between protons and neutrons, specifically actually a neutron becoming a proton. So beta minus decay is the name for that process. Beta minus decay is when a neutron emits an electron and an anti-electron neutrino to become a proton. Good. Okay, so that's what it is. Let's write it down in symbols. So we have a neutron here, and we say it's a neutron emits an electron to become and an electron neutrino to become a proton. Sure. So let's start with the proton just here. It emits an electron, so let's add that one in. Here is our electron. And it emits an anti-electron neutrino, and the symbol for that particle is this thing here. The bar on the top represents the fact that this is an anti-particle, an anti-electron neutrino. Now, this is at the level of a single particle. So we have some kind of neutron becoming a proton, plus other stuff going on, fine. But often we like to think about this transition in the context of an entire atom. So, for instance, we have this atom here, and this thing might spontaneously have a transition to this kind of nucleus here, precisely because there's just been a specific change in one of them. So often we want to write down an equation for how the entire nucleus has changed. In which case we would write something like this. We have some kind of element symbol. So now we're going to use that nuclear notation. Let's say that, in fact, yes, I want to write something else just here. Good. Let's say I have some element X, let's say, and let's say it has a bottom number of protons Z, and a top number, total number of nucleons A. Then we can write what's going to happen. Well, the total, we'll get some new element, quite possibly. We're going to get our electron. Now, for the electron, we sometimes write it with a symbol beta instead, and that is to express the fact that it came from this thing we call beta minus decay. Okay, good. And that thing is negatively charged. And now, because we're writing top and bottom numbers, we're going to try and write some top and bottom numbers here. Well, number of nucleons in a proton, in an electron is certainly 0. It's a different kind of thing. But interestingly, for the bottom, what we will record really is not exactly the number of protons in an electron, but its charge. So because that's a charge of -1, we will write a -1. Okay, good. We know that we got an anti-electron neutrino. So let's put that down. Good. And now we need to look at these numbers here. Well, this new atom that we have is going to have the same number of nucleons as before. We know that because one neutron has become one proton. So the change in the number of protons plus neutrons is zero. There has been no change. On the other hand, a neutron has become a proton. So we do have one more proton than we had before. And so we put Z plus one here. This bottom number has changed from some number Z to being one more. We have one more proton present. Okay, so that's how we can write this beta minus decay as a kind of nuclear decay equation. Now we're going to look at the kind of opposite process in which we have a proton turning into a neutron plus other stuff. Good. So beta plus decay is when a proton emits a positron. Everything gets flipped, basically. A positron. And an electron neutrino. Electron neutrino. For its anti-electron neutrino, now it's electron neutrino. For its electron, now it's positron. To produce a neutron. So everything's flipped. So let's see that. A proton produces a neutron, but to do so, it has to create a positron, which we write like this, and an electron neutrino. This was an anti-electron neutrino, just remove the bar to write an electron neutrino. Okay, very nice. And let's write this in nuclear notation again. So we start with some X, Z, A. We get some new element. Number of nucleons has not changed again because we just changed between protons and neutrons. We have one less proton than we had before. So we put Z minus one there. For the positron, we do everything just the opposite as we did for the electron. So zero here, but now plus one here. And finally, the electron neutrino. And we don't bother, by the way, declaring the numbers for the electron neutrino here, because it don't matter. It has no charge, it has no mass, it has nothing to do with baryons or protons or neutrons. Good. Okay, so this is how we can represent beta decay. And that's probably the hardest one to think about. The others, are, I would say, are generally a bit more simple. So let's look at those now. There's two more that we're going to look at. There's alpha particle decay and gamma decay. So alpha decay is when an alpha, that's a symbol for alpha, an alpha particle breaks off from a nucleus. Good. Okay, so what is an alpha particle? It is two protons plus two neutrons in a kind of clump. Two protons plus two neutrons. There we go. Okay, so for instance, if we have some particle X with a Z here and an A here, what are we going to get? Well, we're going to have two less protons than we had before, so it's going to be Z minus 2. Number of protons plus the number of neutrons has gone down by 2 plus 2, so 4. That's A minus 4 here. And what have we produced? A thing called an alpha particle. And to make both sides of this equation balance, there must be a 2 here. So we have Z minus 2 add 2, that's Z. And there must be a 4 here. A minus 4 plus 4 is A. Okay, very nice. Hopefully that is making sense. And now you're relieved to hear what we're looking at next is probably the easiest one. We're now looking at gamma decay, which is simply when a nucleon releases excess energy. Excess energy. And it does that in the form of a gamma photon. So that there is the Greek symbol for gamma. And the equation here is rather simple. We start with some element x with a z and an a. We have the same element again. We've just given off this thing that we call a gamma particle, which has no protons, no neutrons, no special numbers on it at all. It's just a release of energy in the form of a photon. Okay, good. Now, before we go through some exam questions, something you might be wondering is why do particles decay? Well, one answer, which you will learn as you go through this topic in A-level physics, is it's hard to predict when an individual particle is going to decay, when an individual nucleus is going to decay. However, we can still give reasons as to why certain nuclei are more likely to decay than others. So we're going to look at some causes of decay. And in some sense, you can really reverse engineer the thought here. So why would something go through alpha decay? Well, essentially, alpha decay is where something gives off, where some protons and neutrons break off. So the natural answer is that alpha decay happens when you have too many protons and neutrons. But too many for what? Well, too many to be what we would say stable. So let's be more clear about this. Alpha decay specifically happens because there are too many nucleons to be held together. That's why they'll break away. Held together by what, though? Well, by the force that holds nucleons together. So which force is that? There's too many nucleons to be held together by and don't worry if you haven't heard of this before, the strong nuclear force. Okay, so what is this? The strong nuclear force. This is the force that happens to keep nucleons together. You might not have thought about this before, but if you think about a simple atom or a simple nucleus of an atom, you've got protons and neutrons. In principle, why would they not all just drift apart? Well, it turns out there is a force called the strong nuclear force that holds them together, and you'll learn more about that in later sessions. Now, on the other hand, beta decay isn't about having too many nucleons in general, because you just change one kind of nucleon for another. You change from protons to neutrons. So what's going there is that you must have some kind of imbalance. You must have too many protons or too many neutrons for the atom to stay together. So beta decay happens because there is an imbalance between the number of protons and neutrons. Good. Okay, very nice. Very nice. So we've got this graph on the right-hand side here, which is a graph that represents or allows you to see which kinds of nuclei are likely to decay and in which way they're likely to decay. So you might see this red line in the middle. This red line in the middle is essentially called a line of stability. If your atom has a number of neutrons and a number of protons, this is a plot of neutrons against protons. If it has a number of neutrons and a number of protons such that it sits on this line, then it is very unlikely to decay by beta or alpha decay. However, notice that this line stops. So there's this whole range of possible amounts of neutrons and protons you could have, really high amounts, too many, where you're away from this stability. So what will happen here? Well, if you're over here, your atom is going to decay. It's going to release some neutrons and protons, and it's going to keep sliding down by releasing more and more alpha particles until it eventually reaches a more stable position. Okay, very nice. Next, if we're thinking about beta decay, we should be looking at these regions which are kind of not past where the line finishes, but either side of the line. So, for instance, if we're here, that means that we have more neutrons than we should have to be stable here. So for this, say 40 protons, this is the stable amount. We've got way too many. So since we've got way too many, what's going to happen? Well, we're going to go for a beta decay. We're going to change our neutrons into protons until we get closer to this line. And similarly for beta plus decay, we're over here somewhere. We're going to shift towards this line. Okay, good. So we covered a lot there. How's everyone feeling? Are we feeling good? Are we feeling positive? Feel free to whack a 1 in if you're feeling like this is straightforward. 3 if you're confused. And if anyone has any questions, of course, I can have a go at answering them. 1, okay, nice, very good. I'll keep my eye out in the chat for any questions, but in the meantime, I will give you some questions. Let's do an exam question. Okay, so in this question, we're told that the lead nuclide, so here we have some nucleus, okay, it's unstable and it decays in 3 stages through alpha and beta emissions to a different lead nuclide. So it's lead to lead because it's 82 to 82, fine. For a number of protons is the same as we started with. The positions of these lead nuclides on a grid of neutron number n against proton number z is shown below. Okay, very good. So here we are. Fine. On the grid, draw 3 arrows to represent one possible decay route. Label each arrow with each decay taking place. So it's going through alpha and beta emissions. So there's going to be at least one alpha emission. So let's draw that straight away. Because we don't know if it's going to be beta plus or beta minus yet. Okay, so what would an alpha emission do? Well, it would cause us to say, well, we're starting here at 210. And it would cause us to lose 2 neutrons and 2 protons. Sorry, 2 neutrons and 2 protons. So we'll end up there. So let's just draw that arrow. Well, there's going to be at least one alpha decay, so we know that happens. Now, if you look at this, we essentially have the right number of neutrons and protons now. What we have is that they're mismatched. And how can we reach here? Well, if we trade a neutron for a proton, we lose 1 neutron, gain a proton. If we do that twice, we'll end up where we want. There's going to be 1 beta decay that does this and another beta decay that does the same. Okay, and that is indeed 3 arrows. So it looks like we found the right thing. We have found a possible decay route. Good. Okay. Next question. Complete the following equation to show the beta minus decay of protactinium. Okay, good. So in beta minus decay, does the number of nucleons change? No. So it'll be 2, 3, 3 up here as well. However, let's just label this here for our own sake. We know a beta minus particle has a 0 here and a -1 here. We know that a beta minus particle is an electron, and in beta minus decay, we also produce an anti-electron neutrino. So we put that there. And then we see to get the numbers to balance, we have 92 -1 here. So we must have 91 here. And this makes sense. We have 1 neutron that has now become a proton. That is indeed what beta minus decay is. Good. Finally, this question here, the isotope, I guess Rn is radon, I think. The isotope Rn 86222 decays sequentially by emitting alpha particles and beta minus particles, eventually forming the isotope lead 82206. Okay. Now, 4 alpha particles are emitted in this sequence. Very nice. Calculate the number of beta particles in the sequence. Okay, well, let's start with the thing we begin with, which is this Rn. What was it? 86. And then 222. We're told that there's going to be some number of beta particles. Fine. Get some number of beta minus particles. We're not sure how many yet. We know there's going to be 4 alpha particles that we produce. Fine, each of these has 2 protons, 4 neutrons. And eventually we know that we recover this lead isotope. So that's Pb. Very well. 82 206. Okay, very good. So what can we make of this? Well, we need to figure out how many neutrons there are. Well, let's imagine we start with 86. We see that if we do four alpha decays, then we're going to go from 86 and we're going to lose 4 times 2 protons. So we're going to end up at 76 protons. But we want to get to 82 protons. So have I said that correctly? Yes. From 86, we have 4 times 2, which is indeed 8. Yes, so we're going to go to 76. Good, fine. Then we need to figure out how many beta decays we need to get ourselves back up to 82. So how many times do we need to turn our neutrons into protons to get from 76 to 82? Well, we're going to need to do that 6 times. So the number, because if we add 6, so this is us taking away 8, then what we need to do is we need to add 6. Something very confusing about the maths here, because 86 minus 8, my apologies, 86 is here. I just wrote it wrong. That's why I was confused. 86 minus 8 brings us to 78. And then to get from 78 to 82, we are indeed just going to need 4. Very good. That takes us to 82. My apologies there. Just got scrambled looking at the adding basic numbers. Okay, good. So that's how many we're going to need. We're going to need 4. So we can just put 4 here. And just as a sanity check, let's check all these numbers balance. So here we have 86. On the other side, we have 82. We have plus 8 here from 4 times 2. Minus 4 here from 4 lots to minus 1. And that indeed does give us about 86. So both sides here have 86 on the bottom. This equation balances. So just for the examiner's sake, let's write it very explicitly. Number of beta minus particles produced equals 4. Okay, very good. So the first half of this session, I would say, was mainly quantitative. But now we're going to do more qualitative stuff. We're going to be talking about, as promised, the applications and also the dangers of radioactivity. So far, this has been super abstract, right? We talked about nuclei and we talked about how they might decay in various ways. And when they decay, they tend to produce something smallish that's going to fly off. It might be an alpha particle that flies off the nucleus. It might be just a fast moving electron that we call a beta particle flying away. It might even just be a photon, which is a gamma decay, for instance. Now, it turns out that knowing about these processes gives us kind of engineering applications and medical applications, but also that these processes are essentially firing off of dangerous particles into the air that could cause us damage. So we're going to review all of that now. So to start off with, we're going to look at some basic heuristic properties of these different kinds of radiation. Okay, good. So let's start by thinking about alpha radiation, beta radiation, and gamma radiation. Good. And the first thing we're going to ask about, which is going to be important for applications and for assessing the risks of these things, is we're going to ask about the range of each of these kinds of particles in air. How far can they get through air? Now, alpha radiation is this big, chunky mini nucleus thing trying to move through the air. It's large, it's very likely to bump into things. As a result, it can't get very far through the air. So typically, it's going to go typically around 10 centimeters. Beta radiation is smaller. It's a little electron. Okay. This is going to typically go around 1 meter through the air before being stopped on average. And gamma radiation is this tiny photon. And photons can travel super far. They're tiny things without bumping into anything. And so gamma radiation essentially has infinite range, which sounds scary, but its kind of intensity follows what we call an inverse square law. So as you get further away from a gamma source, it is true that less and less of it will touch you. Essentially because if you're far away from it, lots of it will just miss you, essentially reasoning from facts about angles and distances. Okay, fine. Now let's talk a bit about essentially tests for different kinds of radiation. One kind of test we can do is to put these particles through a magnetic field. So we put them through a kind of magnetic field. How should I draw this? I'll try and draw a horseshoe magnet, maybe. So we're going to pass them all through this, and we're going to see different results depending on what kind of particle they are. Alpha particles have protons, so they're positively charged. Beta particles, beta minus particles are negative, beta plus particles are positive. And gamma photons, they don't have any charge at all, so they won't see any interaction with this magnetic field. So alpha radiation, you can see it because it will deflect like a positive charge. Good. For beta radiation, at least beta minus radiation, you'll know it straight away because it deflects like a negative charge. The confusing case is the positive case because it could still be a positron or an alpha particle. Negative, it's definitely beta minus charge. Gamma radiation is just photon. Photons have no charge, so they will have no deflection, no interaction, no change in their path as they move through a magnetic field. Okay, now let's imagine that I wanted to really block each of these kinds of radiation. Well, for alpha radiation, it's so big, all I need to do is put a piece of paper in the way, and that's going to block it completely. So this is now not going to make it through at all. Good. Whoops. There you go. So blocked simply or absorbed simply by thin sheet of paper. Okay. Now, for beta radiation, it's a bit more difficult to stop it. You're going to need something better than paper. You're typically going to need approximately 5 millimeters of a sheet of metal, for instance, of aluminium. For gamma radiation, again, you're just not going to stop it completely, but you can reduce its effect quite a lot using thick, like very thick layers of lead. Good. And now we're going to talk about ionization. So what is ionization? Well, let's take these particles and pass them through the air as we usually would. And this is basically a dual thing to this range in air problem. So we have these particles, we're passing them through the air. Here is our air particles. Very nice. Good. Alpha particle has a low range in air because it's going to bump into an air particle very quickly because it's a large thing. And when it does bump into an air particle, it is also big and heavy, so it's going to cause quite a big change to that particle. And typically what it will manage to do is to kick an electron off of one of these air particles, causing the air particle here to become charged, for instance, positively charged. And this process is called ionization. Okay, good. Alpha particles do a lot of this because they're big, chunky things. So we say that they're strongly ionizing. Beta particles do a bit of this, but not as much. So we'll say they have a kind of medium power for ionization. And gamma particles will miss air particles for ages and then be immediately absorbed. Do interact with some electron in air particles. So they're very weakly ionizing. Okay, good. These properties, especially these ones at the bottom, are going to, and the one at the top, are going to come back later as we try to understand what different uses each of these kinds of radiation could be used for. Okay, good. Now, just before we do that, let's talk about some of the dangers where all of those different properties are also relevant. So why is radiation dangerous? Well, just as it can damage air particles, and damage is a loaded word, it can change an air particle, for instance, making it into an ion by smashing into it. That's the kind of thing where if it were to happen to cells in your human body instead, ionizing them is something that can kill or damage your cells. So this radiation, this ionization procedure can damage, if it happens in your body, it can damage or kill living cells. Good. Okay. More specifically, it can, for instance, damage DNA. And this is the kind of thing that would typically cause the growth or development of things like cancers or cancer. Good. Okay, so it's very serious, and we need to take lots of precautions when dealing with radioactive materials. And there are many precautions that we can take. So, for instance, we saw that paper would stop alpha radiation, metal would stop beta, and lead will stop gamma. Thick lead is the most kind of thick and dense of all these materials. So thick lead will work for everything to an extent. So we can typically help ourselves by storing sources in thick lead containers. Good. We also never want to touch them directly. We touch them, maybe a few specks go in our mouth, now they're on the inside of our body, where if they're alpha, for instance, they can do a lot more damage. So only handle with things other than our skin, essentially. So things like tongs, gloves, or even robotic machines, for instance. Ideally, all of these. Good. And the last one is pretty simple, just reducing our exposure time. So making sure whatever procedure we do is quick. So we're not around the radiation for so long. So reducing exposure time. Good. Okay, fine. So at this point now, I think we're ready to look at some of the potential applications of dealing with radioactive materials. And the key idea behind quite a lot of the applications is a broad principle that we can use things called radioactive tracers to observe fluid flow patterns. So what do I mean by this? Well, typically, we are somewhere. There is some kind of a barrier through which we can't see. And behind that barrier, through which we can't see stuff anymore, it could be a wall, for instance, it could be the skin of someone's body. There is fluid flowing around. So here's our fluid, and it's flowing around in some way. There's some way we want it to flow. There's some way it is flowing. Those might be different. We want to keep track of how this fluid is flowing, even though we can't see it. And what we need to do is essentially find a way to sense things through this barrier, through this wall. So what we do is we hold something that can detect radiation, something like a Geiger counter. We put radioactive material in the fluid at some point where we have control earlier on, and we watch how it flows. So for instance, maybe this is the pipe here. This is how it's supposed to flow. But maybe let's actually draw the pipe. I think it's instructive. So maybe this water is supposed to flow in this pipe here. But imagine that this pipe actually has some kind of a leak so that some of the water is getting out here. We want to spot that where we put this radioactive material in. Some of that radioactive material will also leak out. And we'll be able to track that because that's something that will still be giving a signal because if we choose the right kind of radiation, it will be able to pass through the barrier and we'll be able to sense it, even though we can't see it directly. So that's the idea. We use radioactive tracers to observe fluid flow patterns. Now, sometimes what we're looking at here is not like a mechanical pipe, but something like an artery, something in a human body. Now, if it's in a human body, we need to be careful because this passing radiation that we're seeing here, be it alpha, beta, or gamma, could be damaging the cells in our body. It's passing through the cells in our body, and we just saw that that's the kind of thing that can cause damage. So when using radioactive tracers on people, we should be aware of this danger. We should use weakly ionizing sources. So sources. And furthermore, we should make sure that these are sources that don't stay radioactive for very long. Now, it might be worth at this point thinking about which of the kinds of radiation are weakly ionizing. And hopefully you remember it's actually the gamma ones. So for a human body on the inside, we'll typically use gamma because it's likely to escape without causing damage. And also it's the kind of radiation that actually can pass through the skin barrier and be detected on the outside. Okay, so there are some other applications of radioactivity. So for instance, I'll write them in here as well. So we have like medical tracers, as we saw before, just here. We have things like detecting cracks in pipes, so crack detection is pretty cool. But also, since radiation is the kind of thing that can cause damage, we can actually use it to kill bad cells in our body. So we can use it to try and kill cancer cells. So some cancer treatments involve firing radiation at already damaged cells. Also testing the thickness of materials is another. Testing thickness. The amount of radiation that gets through, we saw it depends on the thickness of the material it's going through. So you can actually test the thickness of materials by seeing how much radiation is passing through them. Good. So at this point, I will ask, how confident are we all feeling? And does anyone have any questions? We have just a couple of exam questions to go through to finish off the session after this. One, very nice. Okay, that's fantastic. I will keep an eye on the chat, so just let me know if there are questions. So, last couple of exam questions. State which type of radiation, alpha, beta, or gamma, produces the greatest number of ion pairs per millimeter in air. Okay, so I'll open this to the chat. Which kind of radiation produces the greatest number of ion pairs when passing through air? In other words, does the most ionization? Can anyone in the chat tell me which they think that'll be? Or just take a guess. Okay, so I'll jot this down. The most ionizing type of radiation was alpha particles, this big heavy kind that keeps bumping into things and doing lots of damage. Okay, which kind can be used to test for cracks in metal pipes? Well, to test for cracks means that it's going to have to pass through some barrier, for instance, the ground to reach us. So here's our pipe. Here's the flow. We want this to pass through the ground. So it needs to be weakly ionizing. It needs to be able to get far and be hard to block. So that's going to be gamma. Okay, next question. Specific radioisotope sources are chosen for tracing the passage of particular substances through the human body. Why is a gamma emitting source commonly used? Okay, it's something that we've already talked about. It is the least ionizing. So will cause the least damage inside the body. Remember, it's a tracer, so it's beginning from inside the body. That's going to be important in a second. We're going to be asked a different, more interesting question. Okay, good. So, next question. State and explain two precautions that should be taken when working with a sample of magnesium in a school laboratory. Earlier in this question would have been told that this is indeed a radioactive particle, by the way. Okay, so what can we do to deal with a radioactive particle safely? Well, a few things. So which should we do? I think we can go for let's go for storage. So I think keeping it in a thick lead container, that's a classic. So store the sample in a thick lead container. Good. Next one. Use gloves or tongs when handling the sample. Classic. Very nice. Very good stuff. Okay. Next question. Discuss which of the two types of radiation, beta minus or gamma, emitted from a sample of magnesium would be more hazardous. Now, this is interesting. I'm going to give just 20 seconds to have a think about the answer to this question, what you think it could be. So I'm just going to pause. If anyone has a guess, feel free to put it in the chat. I think this one's a super interesting question. Interesting. So you've said that gamma will be the more dangerous, and you're absolutely right. And this is very strange because we just did this tracer question. And in the tracer question, we were essentially being asked about the human body. So here's our human body. Fine. Very roughly. And we were being asked before about which kind of source we should use inside the body. And inside the body, the safest thing is something that's going to get out. And so the safest thing is going to be gamma. And the dangerous thing is going to be beta. So gamma source can get out the body. However, now we're dealing with a sample which is actually far away from us. It's over here somewhere. Here's our magnesium. And so what's going to be more dangerous? Well, beta radiation is stopped by a meter of air. So beta radiation is going to get to about here and then stop. So long as you stand far away from it. Whereas gamma radiation can pass through forever. So it will still reach us and cause us some damage. So you're absolutely right. The answer is gamma. When the source is outside of your body, the most dangerous is often gamma radiation. Very good. Nice answer. So gamma is most hazardous. Hazard or hazard? Hazardous. Well, they wrote it hazardous. Yeah, hazardous. As it has the greatest range in air. Okay, perfect. Well done. Really good stuff. So let's just review what we've seen. You should now be able to understand how and why radioactive decay occurs. You should be able to analyze the properties of the three radiation types, and you should understand the practical applications of radiation. So hopefully that's all making sense. And I'll just finish by asking if anyone has any questions for me. We have a couple of spare minutes, in fact. So yeah, certainly if anyone has any questions, just let me know. And thanks everyone for listening and for any participation in the chat. Okay, so I can't see any more questions in the chat. So I think that's probably a good place to leave the session. Thanks very much again to everyone for coming. Thanks to anyone for watching who is watching this recording at a later date. And I'll just say good luck with the rest of your A-level learning, and I will catch you at the next one. Okay, bye.